Howdy, it's Danny. This is lecture number 12. This is the lecture on fossil hominoids. Well, really, I'm going to cover a lot of different fossil apes and ape relatives, human relatives, and get started moving towards the story of human evolution as it's understood now. See, pictured here, we have Lucy, Artie, Piltdown Man, and Tong. We'll learn about these guys in this lecture and the next one. So, to start off with, I want to give you this phylogeny, this phylogenetic tree of human relatives. And I'm going to proceed through this phylogeny much like I did with the phylogenetic chart from the last lecture. That is, I'm going to indicate groups and talk about them. So, to begin with, well, the group that we're talking about hominoids, hominoidea, the apes, including gibbons and siamangs, orangutans, gorillas, chimpanzees, humans, and australopithecines. The first ape, well, a good guess is that it was proconsul. Proconsul would have been in this group here. This is a family identified as Proconsulidae. This genus, Proconsul, and this family, Proconsulidae, they were around around 20 to 15 million years ago. That's when the genus Proconsul was around. It would have had some ancestors before that on this chart. They did not have tails, so that is one ape-like trait they had, but that's not completely diagnostic of apes, as you know, because there are some tailless monkeys, or some monkeys with very reduced tails. The thing that seems to mark them as apes is that they had ape-like shoulder girdles and ape-like teeth, but they still did not have the adaptations for brachiation that are considered typical of apes. In fact, last time I spoke with Adrienne Zillman, the author of your coloring book, if you have it, I mentioned Proconsul to her, and she just went, it's not an ape. So, well, to say the least, Proconsul's position as the first ape is arguable, but it still is occupying an ancestral spot on the ape family tree. Here are some reconstructions of Proconsul. I like these different versions of it. It was an African animal, so apes evolved first in Africa, and then its close relatives quickly spread to Europe and Asia. And here we have reconstructed locomotion for Proconsul. It probably walked on its hands like monkeys, that is, on its palms. Contemporary apes walk on their knuckles instead. So, you will recall that hominoidea, the extant apes, the living groups of hominoidea at least, the two living families, were Hylobatidae and Hominidae. And Hylobatidae is thought to have drifted, you can see here on this orange line, away from Proconsul and its relatives starting about 15 million years ago. So that's pretty close to what's on this chart here. Ponginae, which was part of family Hominidae, remember, Ponginae was a subfamily of the family Hominidae. Ponginae split off from the line that would lead to us about 10 million years ago. So here we would have a split, this half of it leading to gorillas, chimpanzees, australopithecines, and us, and then this half leading to the orangutans and their relatives. That split happened about 10 million years ago. So here we're identifying Ponginae as 10 million years old. That's close to it here. This is all red, just like this, but you'll just don't worry about it. I probably won't test you on these dates. So the only living Ponginins, or members of Ponginae, are orangutans. But they had a lot of relatives that existed for a long time. We can include Encaropithecus, Sevopithecus, and Gigantopithecus among these. Gigantopithecus, which survived until relatively recently, less than 1 million years ago, was actually the largest known ape. That's him in the background. This is me, of course. This is at the Museum of Man in San Diego. Gigantopithecus is actually only known from jaws and teeth. And they maybe lived starting about 6 million years ago and may have lived up until about 100,000 years ago. They might have been gone way before that, though. The jaws and teeth, it's kind of an interesting story how Gigantopithecus came to the attention of science. Its teeth, fossilized teeth, had been recovered uh, from fossil deposits in China for a long time, and they had often been sold as dragon's teeth, uh, that is, as a medicinal ingredient for tea or for tinctures and powders. And it was in the context of the Chinese traditional medicine market that paleontologists first found Gigantopithecus teeth. And they've reconstructed the rest of the body just basically from the teeth and the jaws. Uh, so most of its body is actually quite speculative, but its teeth and jaws seem to indicate a relationship with the orangutan group. And so in this reconstruction here, it's kind of built like a giant, mostly bipedal orangutan. They could have been up to 12 feet tall, or 9 feet tall, perhaps. I'm thinking of, when I say 12 feet, I'm thinking of course, Sasquatch, which is kind of what the Gigantopithecus looks like, a big Sasquatch, right? A Bigfoot, and probably an imaginary creature, unfortunately. Um, well, anyway, the Bigfoot people really love the idea that Gigantopithecus is Bigfoot, and that Bigfoot is surviving individuals of Gigantopithecus or populations in Canada, of all places, and the U.S. Santa Cruz, for instance. Anyway. Here's another orangutan relative, Cevapithecus. It was alive around 12 to 8 million years ago. This reconstruction of it shows it as still basically a quadrupedal sort of animal, adapted for the trees, though, gripping those branches quite effectively. A good deal more slender than orangutans, but certainly an ape. So this stretch here, between the last common ancestor of the orangutan line with our line, we don't really know what's going on here. There is a dearth of information regarding the evolution of the African apes other than humans. We know a lot now about Australopithecus and early species of Homo, but that's only because we've been looking really hard for them. We don't know really anything about the evolution of gorillas or chimpanzees. Uh, One reason for this, perhaps, is missing fossils. In fact, what these pictures these are the only known gorilla fossils. They're dated to about 6 million years ago. Uh, uh, about 6 million years ago. The part of the problem is that we've been looking in very recent deposits, right? The molecular clock estimates that human ancestors diverged from other African apes about 5 million years ago. So we've only really been looking for stuff starting at the 5 million mark. And if we want to understand the evolution of chimps and gorillas and the ancestors that chimps, gorillas, and humans have in common, then we have to look a little bit further back. But that's not where the sexiness is. That's not where the fame and the late night show on the Discovery Channel is. What's going to get you noticed is if you're doing research over here on these guys, and sometime since the 5 million year mark. Well, that's actually debatable. But so these gorilla teeth here, these were actually just discovered in 2012, and I want to tell you my own idea about why we don't have any fossils of gorillas and chimps ancestors, and that is because I think every time we find one, we try to argue that it's a human ancestor. Because again, that's where the appeal is. That's where the popular appeal is. Looking for human ancestors is sexier than looking for chimp ancestors. Looking for human ancestors, something that's going to say something about where we came from versus where gorillas came from. It's just a matter of what's going to capture the interests of not only the popular media and the people who consume that, but also the interests of the scientific community. So when we're trying to figure out the trajectory of human evolution, there's always a lot of talk about figuring out what was the first organism on our line after the human-chimp split. Let's go back for a second here. So this would be the human-chimp split, this joint right here. Over here is to the African apes, and over here is to us, right? Well, over here is to the chimps, and over here is to us. So there's always a lot of emphasis on trying to figure out what was the earliest thing right here, because we want to understand this, and we want to understand what goes on with all of this. So we want to try to get an idea of what were the creatures here like, and what sort of world were they living in, so that we can say something about what motivated or what caused the adaptations from here to here, right? So, with that in mind, here is one of 3 recent candidates for earliest human ancestor. That is to say, one of the candidates for the earliest ancestor of humans after the human-chimp split. Sahelanthropus chadensis. We can just call it Sahelanthropus because they only know of one species so far. It was uncovered between 2001 and 2002 in Chad, and the people who were doing this work were Michel Brunet, this fellow here, a French paleoanthropologist, and a team of Chadian researchers. So basically all they found was one cranium. This is a reproduction of the cranium. They named this individual Tumai, and you can see there's some issues with Tumai. He's very squished up. Let me just get the rest of this up here. He's very squished up. And these reconstructions were done with computers. The actual Tumai is this, basically. Very squished up, slanted, flattened skull. Right, bones, after they fossilize, they become part of the earth and they're subject to the forces of the earth. So there were geological forces acting to squish this up and break it up. So the skull itself has been dated to 7 million years old. That's from the strata that it was found in, which means that Sahelanthropus lived about 1 million or 2 years before the molecular clock estimates that humans and chimps split off. So that would seem to indicate that it is possibly a relative of the common ancestor of humans and chimps. However, Brunet and his group argue that Tumai actually occurred after the human-chimp split and is therefore to be considered a human ancestor, that it is not ancestral to chimpanzees. And the reason they argue that it's a human ancestor is because of the position of the foramen magnum. Now, I talk about this at length in the second bone demo, so you should go definitely check that out and watch that if you haven't watched it by now. So here is an image with the foramen magnums. I don't want to go too much into detail with it here at the slides because it's really better observed. It's basically just the hole where the spinal column connects to the skull. And something to note is that in some species, some primate species like baboons, the position of this hole can change as you're growing up. So in humans, the hole is directly underneath the brain case. On chimpanzees, it's further back because chimpanzees have a different stance than humans. And on a quadrupedal animal, chimpanzees are knuckle walkers, remember, so they're not quite quadrupedal. They're sort of angled at their body is positioned at an angle. But in quadrupedal animals like dogs, cats, horses, etc., the hole is on the back of the skull. So in Sahelanthropus, Brunet argues that the hole is underneath the skull, but that's problematic because, first of all, Tumai is squished up. Second of all, Tumai might have been a juvenile, and that hole might have been on the way to a different position on the skull. And so we can't really tell if Sahelanthropus has got a chimpanzee-like foramen magnum or a human-like foramen magnum. We need more fossils of Sahelanthropus before Brunet's claim can be properly evaluated. I heard they have some now. And anyway, here again is, this is from Brunet's article demonstrating the angles of the foramen magnum, which would be here and here and apparently here on Sahelanthropus, here on a chimp, here on another chimp, demonstrating the angles of the foramen magnum to the basically to the face, to the orbital plane, to the alignment of the eyes. So you can see that in chimpanzees, who are knuckle walkers, it's quite a sharp angle. In humans, it's an obtuse angle. Brunet's reconstruction with the computer shows a slightly obtuse angle, and that's why he thinks that Sahelanthropus may be ancestral to humans rather than being ancestral to chimpanzees or humans and chimps. I personally think he looks like a chimp or a gorilla. It'd be interesting if somebody would consider that Sahelanthropus could be an ancestor of chimps or gorillas and try to learn something about their evolution from him, perhaps. We'll see what happens with him. Another contestant for earliest known representative of the human lineage after the human-chimp split is Auroran tugenensis. We can just call them Auroran. Auroran was dated to sometime between 6 and 5.8 million years. It was discovered in 2000 in the Tugen Hills of Kenya by Martin Pickford, a British paleoanthropologist, and Brigitte Senu, who is a Belgian paleoanthropologist, I believe. Basically, all they found a few pieces of mandible, a little bit of pelvis, some teeth. They found some humerus, chunk of femur. Where's the humerus? The humerus is not shown, but they found femurs and some finger bones. And the thing that's of interest here is the femur and its ball joint, because they claim that the femur and the ball joint, where are we here? Here it is. Here is Auroran's femur and its ball joint there, ball joint. They claim that this femur and this ball joint here is similar to that of a biped. Where's a biped? This is a biped, and this is a biped. And so the idea is, if they can show that Auroran was bipedal, that it walked on two legs, then that would definitely, perhaps, put Auroran in the human lineage rather than the lineage leading to chimps. But the evidence is pretty sketchy because, as you can see, some of the diagnostic pieces are missing. So you can look at a human here, and a human has a sort of upright protuberance here. This here is where your femur would plug in to your pelvis, and this would be sort of the top of your femur right below your hip. So you can find this point by touching the blade of your hip, your ilium, and then moving down to find the bony protrusion at the top of your thigh on the side there, kind of forward of your buttocks. And you can see that this protrusion here has a more or less kind of straight shape, versus a gorilla, where it's got a curve kind of inward. On a chimp, it's got a curve kind of inward. So the curves inward are accommodations for the particular muscle arrangements and tendon arrangements, ligament arrangements rather, that these knuckle-walking creatures have, whereas this represents an accommodation for the musculature of a bipedal creature. Pickford and Senu are claiming that this broken femur represents, or presents rather, a structure more like this than like this, but you can see the problem. The protuberance is broken off. We don't know what it looks like. The evidence is pretty sketchy. And again, I'm just showing the chimp compared to the orangutan, compared to this guy. I kind of wonder if Auroran is not an ancestral chimp or a proto-orangutan rather than a human ancestor. So these two, Sahelanthropus and Auroran, are potentially groundbreaking if the claims made by their discoverers are correct, right? Because they're both showing evidence for bipedality. Humans, the position of the magnum foramen is because we're upright and bipedal. And so if you have a magnum foramen like us, you might be bipedal like us, right? Auroran, the claim is that Auroran was probably bipedal because of the shape of the femoral head here. So if we accept that bipedality is evidence of being in the human lineage, and if we accept that either Auroran or Sahelanthropus are bipedal, then what that means is that the molecular clock that has been used to calculate the human-chimp split is wrong. And in fact, I don't have this updated in my slide, but just last year there was some more research revealed that recalculated the molecular clock as it pertains to humans and chimpanzees, and they actually put the last common ancestor of humans and chimps back to about 7 million years. But these dates get updated and changed all the time. But there's issues with this. The first issue is that the evidence that Sahelanthropus or Auroran were actually bipedal, that's actually quite weak. We can't say for sure. And even if they did turn out to bipedal, to be bipedal, then that does not necessarily mean that they are in the human lineage. It could be convergent evolution. They could have been a relative of chimpanzees that then convergently evolved into bipedalism like we did. And an example of this would be Oreopithecus, which is an ape that lived in Italy between 6 and 7 million years ago, and as shown in this reconstruction, it was bipedal. Oreopithecus means swamp ape, and it might have been bipedal because of its wetlands habitat. It would have been standing up, maybe even in shallow water, and it would have been foraging on hard-to-reach objects that knuckle walkers might not have such a good time getting to. So Oreopithecus is, relatively speaking, not all that close to humans, does not share a common ancestor with humans, not a recent common ancestor anyway, not since the human-chimp common ancestor, but nevertheless evolved to walk on two legs like a human. This is convergent evolution, and it's an argument against Auroran and Sahelanthropus being in the human lineage. Now, there was a third contestant for the earliest character on this side of things, the earliest one on this blue line, and this one looks pretty good, but it's got its own sort of political difficulties in a way. And this character is Ardipithecus. Ardipithecus was discovered in 1992 by Tim White, this guy, in the Awash region of Ethiopia. And it took him 2 years of study of the fossils to identify it as a new genus. And that's fine. You know, it takes time to do this work, and it takes time to make these determinations. And he announced the find, but this is where the problem comes in. He did not share the fossils for 13 years. This is Tim White, professor at Berkeley. He did not make the fossils themselves available to other scientists for study for more than a decade. Now, I mean, why did he do that? Maybe because he needed to be sure before he put his reputation on the line? That's possible. Also, he might have just been sort of monopolizing the research potential of Ardipithecus. Because if he made the fossils available to other scientists, they might scoop him. It's a cutthroat world. But the reason I bring that up is because actually it's against the notion of science as a community, right? He was making claims during this decade period, but nobody could check his claims. There was nobody who could double check. And he still doesn't release the fossils at all. He allows people to come in and examine them now, but they don't go anywhere. Anyway, Despite all this, Ardipithecus is really truly a convincing candidate for the earliest known human ancestor after the human-chimp split. The specimen that Tim White found initially was Artie. Here's a reconstruction of Artie, sort of a strange-looking creature. Artie was Ardipithecus ramidus and would have lived about 4.4 million years ago. That would have been after the molecular clock estimates of human-chimp divergence, so that's a point for Ardipithecus because it agrees with other kinds of data. Remember the blind sages working together to figure out the shape of the elephant. Well, here's fossil evidence that jibes with the DNA evidence. Later, another species of Ardipithecus was discovered called Ardipithecus cadaba. It was originally identified as a subspecies and was named Ardipithecus ramidus cadaba, but now it's considered its own species, Ardipithecus cadaba, and it's even older. It lived about 5.8 million years ago, which puts it slightly before the divergence of humans and chimpanzees, according to one version of the molecular clock estimates. So possibly Ardipithecus genus might be the common ancestor of genus Homo, genus Australopithecus, and genus Pan, the chimpanzees. Or maybe the molecular clock data needs to be checked again. Anyway, so the bonuses of Ardipithecus agrees with molecular clocks. It had curved finger bones, which indicate a semi-arboreal lifestyle. So it was a transitional creature. These finger bones, you can also see a little bit of the curvature here with some of them. The curved finger bones mean that it was still in the trees. And this is what we would expect of a common ancestor or recent divergent ancestor, recently diverged ancestor rather. We would expect them to still be semi-arboreal. Maybe hanging out in the trees at night to hide from lions, and then coming down to the ground and walking around during the day. Ardipithecus was certainly bipedal like humans, and we can tell this easily from the shape of its ilium. We'll talk about that shortly. Also, like humans, Ardipithecus demonstrates reduced sexual dimorphism. That means that unlike chimpanzees and unlike gorillas, Ardipithecus males and females were about the same size, and their canines were about the same size. In humans, males and females are about the same size, and we don't have any skeletal features. Well, I mean, there are skeletal differences between men and women, but there are none that seem to be very pronounced and geared towards display adaptations, like canines are for chimps and gorillas especially. So that seems to indicate that Ardipithecus is also on the human side of the human-chimp group. To back up a little bit, Ardipithecus is a good one. Ardipithecus would have possibly given rise to a group called Australopithecus. And I'm going to talk about some of the finds relating to Australopithecus now. Australopithecus is certainly the best known creature after the human-chimp split. It's certainly an organism that occurred after the human-chimp split. Australopithecus is not ancestral to chimpanzees. It's ancestral to us. So let's go over some of these Australopithecines. I'll explain the group as a whole in more depth shortly, but let's talk about some discoveries. The first Australopithecine that was discovered, and strictly speaking, you could call Ardipithecus an Australopithecine, because it's very similar to these creatures, even if it's not in the same genus, Australopithecus. I know all this taxonomy is quite confusing. At any rate, just try to keep up with it. It won't be too important, but it does help you keep track of the story. So the first Australopithecus identified was the Tong child, and it was this front of a skull here. The reconstruction here of the Tong child puts him to be, quite a small guy, maybe a year or two old, semi-arboreal. We don't know all that yet, because initially all that was found was the skull, the face, the mandible, and this endocast. This is, though the cranium is not preserved, the stone that filled the cranium, that replaced the brain, is preserved. So what we have is a cast of the shape of little Tom's brain. This is not his actual brain turned into fossil, as this is sort of his actual bone turned into fossil, although the fossilization process tends to replace organic materials with inorganic materials. At any rate, this is not his actual brain, but we can learn a lot about the shape of his brain from this endocast. It's very interesting. This is just what I just told you. His discoverer was Raymond Dart, who was an Australian anthropologist working in South Africa and living in South Africa in the 20s, of course. He was teaching at the University of Witwatersrand. I hope I said that right. I don't actually speak Afrikaner. But he noticed that Tong's teeth were quite human-like, even though his brain was still chimpanzee-like. And for that reason, Dart suggested that Tong's species was a human ancestor. This happened in the 20s, so this is long before Sahelanthropus, Nauroran, and Ardipithecus. This was big news. So in the 20s, this is the reason why this was big news. In the 20s, the consensus about human evolution was that large brains evolved first, and then bipedal locomotion and our typically human small teeth. So you often see images of a brutish caveman, right, who has a kind of brutish body, but is wearing clothes and carrying a club. So he's smart, but he's stuck in an ape body, right? That was sort of the image of human evolution in the 20s. Tong was opposite to that. Also, the 1920s consensus thought that humans must have evolved in Europe or in Asia. So the broadest way to explain that misconception was because of the racial biases of the people who were doing the research. It just did not occur to them to look in Africa. No Homo fossils had been found in Africa, so they didn't think that humans came from there. But the reason no Homo fossils had been found is because nobody was looking. They were all trying to dig up Europe or Asia to figure out who the first humans were. They actually had a little bit of reasoning for this. It was it was logical in context, but it was wrong reasoning. The reasoning was, get this, that since Europe and Asia exhibited something called civilization, that is, specialized modern societies that were not quote-unquote primitive and were not beholden to traditions, although they are, but since Europe and Asia hosted modern societies, it stood to reason for the researchers of the 1920s that humans had been in Europe and Asia longer than they had been in Africa. The idea was that people in Africa lived simpler lives or quote-unquote more primitive lives because they were still sort of in a sort of cultural infancy and just hadn't had time to develop into a real civilization yet. So clearly, if you wanted to find the first humans, you would have to go to where they had been the longest, and you would look in Europe and Asia. That was the consensus in the 20s. And just like I said, the only reason there were no Homo fossils found in Africa was because no one was looking. But Tong had a chimp-like brain and a human-like body. Well, human-like teeth. So that kind of becomes a metonym for his body in these arguments that people started having. Tong was in Africa. But there was also this other character on the stage called Piltdown Man. Piltdown Man was discovered, quote-unquote, in England by Charles Dawson in 1912. He claimed to have been given the skull in 1908 by a quarryman. The skull had a big cranium, but an ape-like jaw. It was the exact opposite of Tong. Tong, who had a little brain and a human-like jaw with human-like teeth. Piltdown had a big brain and ape-like teeth. And so this was tailor-made to fit the consensus of the 20s, that the large brain evolved first and then the body changed. And so Tong was not accepted because Piltdown Man was there, Piltdown Man was very popular, and plus there were these kind of structurally racist presuppositions presuppositions about where humans came from. So, as I said, anthropology loved Piltdown. He confirmed the theories at the time. This is Piltdown. Tong contradicted Piltdown, and so the consensus of anthropologists when Tong was discovered in the early 20s was that Tong must have been an ancestor of chimps and not humans. However, Raymond Dart did have one ally. Oh, Raymond Dart was mocked and he was made fun of, and he was just not taken seriously at all. One fella who took Dart's side was this guy, Robert Broom, who examined Tong and agreed that Tong was closer to humans than chimps, or at least he was on his way to becoming a human, evolutionarily speaking. And so Broom went out and did research. He did more research, he did more excavations, and he found more Australopithecine fossils. The site where he found these at was Sterkfontein. This is all again in South Africa. One of the examples he found, he named it Mrs. Please, and she became sort of jokingly known as Tong's mother. She was a robust Australopithecine, I believe. No, he found the first robust Australopithecines also. We haven't talked about them yet. We will. The confusion will be lifted soon. So here, these are like, shall we say, flashcards, collector's cards for important fossils. And I will present several pages like this over the next couple of lectures. So here's Tong again, when he was found, where he was found, and then his fossil ID. Here's his species, and then when he lived, when he's been dated to. And then here are some notes that of importance. So he had an interior foramen magnum. That means he was possibly bipedal. Based on his dentition, he was about 3 years old. Here's Mrs. Please, who was an Australopithecus africanus, an adult of Tong's kind, discovered in 47 by Broom at Sterkfontein. Her number is STS5. She would have been alive about 2 million years ago, so actually 800,000 years after Tong died. But they would have been the same species. It's a very nice skull, as if that's important to note. But here is another one of Broom's finds. This is the first robust Australopithecine that was ever found. I'll talk about the differences between robust Australopithecines and other Australopithecines later. But this species is Australopithecus robustus. It was found at Schwarzkranz, and it was dated to about 1.8 million years ago. So this is an even younger species, an even later species. And it was similar to Australopithecus africanus, of course, but had different feeding adaptations, which we'll talk about when we talk about the robust Australopithecines. But this is a good slide to take notes of if you want to kind of keep track of where human ancestors are living at certain times so that you can string the story along through space and time. So the two kinds of Australopithecus that were identified by Broom and Dart can be called graciles and robusts. So the two flavors. Both are usually considered members of the genus Australopithecus, but sometimes, as I will note now and later, the robust ones are given their own genus called Paranthropus, but it doesn't really make any difference. They are still Australopithecines in general. If you're talking about Australopithecus, you're talking about a genus. It must be italicized with a capital A. Australopithecine is the generic term for creatures within this genus, for creatures within Paranthropus, if that is its own genus, and for creatures in the genus Ardipithecus, which we've already discussed. There are several kinds of gracile and robust Australopithecine, so they actually had quite a bit of diversity amongst each group. And just to review, Tong and Miss Please were gracile Australopithecines of the species Australopithecus africanus, and SK48, the one that was on the previous slide, was a robust Australopithecine of the species Australopithecus robustus. So one way to tell the difference is the dentition, the teeth. If you've got your coloring book, page 520 will explain this to you. The graciles, and also you can look at the bone demo, I'll go over it as well. The gracile Australopithecines had smaller, non-specialized teeth. very similar to human teeth. Whereas the robusts had specialized grinding teeth. They had big grinders. Also, you can tell some differences in the jaw muscles. And although we don't have their muscles, we do have the attachments on the skull where the muscles would have connected to the bone. And you can tell on the robust face here that he's got a large zygomatic arch and that he's got this sagittal crest here, this fin, and these big cheekbones. Versus the gracile has smaller cheekbones, smaller holes. The muscles would run through these holes, so we know the robust ones had bigger cheek muscles, and nothing on top of the head here. So what these mean is that the robust probably had to do a lot of chewing of plant matter, whereas the graciles were more omnivorous and ate all kinds of things. So here's a note on their taxonomy. Well, like I said, let's just put all this up. Like I said, usually you can consider everything here, from here up until we get to here, where Homo starts. So all these guys, you can usually just consider them all members of genus Australopithecus. But some people like to give the robust ones their own genus, and they certainly are different kinds of animals. And when they do that, they give them the genus designation Paranthropus, represented by this purple line here. So all these guys and this are robust, whereas these guys here are graciles. The robusts evolved actually from the graciles. So these large plant-eating, big-boned Australopithecines actually are the descendants of gracile Australopithecines. And they evolved from them about 3 or 4 million years ago, and they were extinct by 1.5 million years ago. So I want you to note that since the robusts evolved from Australopithecines, and since humans also evolved from Australopithecines, we can think of the genus Homo and the genus Paranthropus as sort of sister taxa that share a common ancestor, the genus Australopithecus. It just depends on how you look at it. So nobody took art seriously, as I told you, but people did take brooms seriously, and more Australopithecine fossils began to be found over the course of the 1920s and the 1930s and the 1940s. And so, finally, in 1956, after all this evidence had been building, that finally, over 30 years, all this evidence had been built up that finally supported Dart's claim that Australopithecus was a human ancestor. In 1953, anatomists revealed that Piltdown was a hoax. Charles Dawson had been dead already, died famous in 1916, had fabricated Piltdown. What did he do? He took an orangutan's jaw and broke off the ramus, broke off this part, and just stuck it with a human cranium. And then he filed down the teeth in such a way as to make it look like they had been broken by time, but really he was just obscuring the teeth and the way that the jaw connected, and therefore making it impossible to identify the teeth as the teeth of an orangutan, and also making it impossible to verify that the jaw was actually attached to the cranium. This is what you call a chimera, which is when you take two different animals and stick them together. It was a hoax. So there's a good question, right? Were the anthropologists just stupid? Why couldn't they have figured this out? I thought they were experts on anatomy. Well, here's an Onion article. I stole this from the Onion. I didn't use their headline, just their picture. Right? It's kind of like that. Could they just be wrong? And then they wake up one morning and say, hold on. Well, no. They weren't just stupid. There was a lot of things going on working for Piltdown. Remember, science is social, so it's never really just a matter of figuring out what the truth is. There's always something else impinging upon it, whether it's personal biases or a political situation. So the first thing to keep in mind is that the public loved Piltdown, right? The English loved thinking of a Piltdown man who was found in England as the first human. They thought that was great that humans had been born in England. How amazing is that? And then there were lots of very well known and very serious scientists who supported Charles Dawson. Um, Many of those guys had their reputations built on Piltdown. They had gotten their PhDs doing research on Piltdown, and Piltdown had become essential to their own theories. So they had a lot of financial and social and even theoretical capital invested in him. And then finally, the jaw joint was broken, so it was unclear how the two pieces fit together. So there was a lot riding on Piltdown, and in any situation where there's a lot riding on something, people are generally pretty reticent to let things change. But eventually things did change, and Australopithecus was finally considered seriously as a human ancestor. And like I said, there have been stranger things. I've already told you a little bit about Chalicotherium here, who was uncovered. Well, it was not originally uncovered by Baron George Cuvier, but it was George Cuvier who figured out that all these pieces that didn't look like they went together, like this horse's head and these predator's hind limbs and these claws on this front leg and this weird long front limb, they look like they didn't go together, but they actually did. So very strange things have been found in the paleontological record, and so even if it couldn't be verified that the jaw and the cranium went together, somebody with a reputation says he found them together, people will tend to believe them. And again, fossil evidence is always pretty sketchy. Artie's here, and this is Lucy, another famous Australopithecine. And these guys are about as good as it gets. Artie and Lucy are really excellent skeletons, and they're nowhere near complete, really. So let's talk about Lucy. Lucy is probably the most famous Australopithecus nowadays, because of her ilium here. We'll talk about this, but this ilium is what made her famous. She was discovered by Don Johanson in 1974, also in the Awash region of Afar in Ethiopia. And she was dated to about 3.2 million years ago. The really important piece here was her pelvis. They got one finger bone, which was a little curved. So this pelvis here indicates that she was bipedal, but this finger bone indicates that she was probably still hanging out in trees at night. And this tibia, this part of the tibia right here, and her pelvis, indicates she was a biped. Should say locomotion. So let's do some pelvic anatomy first so that you can understand what's going on with Lucy. And if you like, you can go back and look at Artie, because Artie has a rather nice ilium too that places him close to us, at least as a biped. So your pelvis has four parts. There's the pubis, which is in front. That's behind your pubic area. It's pretty easy to find. You just press around in there until you find the part of your pelvis that's underneath your flesh. There's the ischium, which is what you sit on. You can find that underneath your hip bone, underneath the curve of your hip bone, kind of right below your buttocks. Then there's the acetabulum, which is where your femur plugs into the pelvis. And there's the ilium. The ilium's the important part. All of it known together is the innominate, which means nameless. But this ilium here, this is your hip bone. You can locate it by pressing on your hips and feeling that broad curve that goes from front to back on your sides. That's the important part for Lucy here. So what do ilia do? Ilia is plural for ilium. What do they do? Well, this is where we do muscle attachments. This is where the gluteus maximus attaches. And you can see here in a human, this curve of the ilium serves as not just an attachment for the back here, but also as an attachment for the glutes. Check out the chimp. The chimp has a very differently shaped ilium. See, the human ilium is scoop-shaped like that. The chimp's is blade-shaped. And his gluteus maximus attaches to a shorter area on his pelvis, right? So that basically means less attachment, less of a skeleton to push and pull on, so less strength per se. This here is Hamdallah Aykutlu. He's a bodybuilder from Iran. He has won many prizes for his striated buttocks. So the reason I show him to you here is to identify his gluteus maximus, and if you follow the striations on his buttocks, you can see the sort of the direction of his gluteus maximus. Well, first of all, it's a very large muscle, and you can see that it is stretched from points over here towards points in here underneath this muscle. You can also see a similar sort of thing with this chimpanzee. This guy's name is Mongo. He just happens to be a hairless chimp. He just happens to have propecia, which makes him very convenient for showing muscular anatomy. Look at his arms. But let's look at his back. Close up here. Again, this bracket is broken. I'm not sure how that happened, but this is his gluteus maximus. This large muscle is his gluteus medius. In chimpanzees, the medius is actually larger than the maximus. The names medius and maximus, of course, refer to their size on humans, where the gluteus maximus in a human is the largest muscle. But you can see that on Mongo, his gluteus maximus is not as well developed, and it certainly doesn't have the size, and definitely not the striations of Hamdallah Aykutlu. One more time for comparison. And again, obviously, don't really compare the striations. Aykutlu had to work very hard to make his buttocks like that, and Mongo's probably never bothered to work out. But what you should notice is the relative size of this muscle to other muscles. The reason why, well, one reason why we need such large gluteus maximuses is it supports our torso as we're moving bipedally when our torso is upright. This muscle helps to keep us up, and it also swings the leg forward. On the chimpanzee, he can't swing his leg forward quite as well. He sort of has to angle his leg to the side a little bit, and his body will tend to rock back and forth as he walks. If he walks on two legs, that is. So for comparison here, here's an Australopithecus, an Australopithecine pelvis, a chimpanzee pelvis, and a human pelvis. So you can see where somebody with a pelvis like Lucy's is pretty clearly a biped, pretty clearly on the human side of the human-chimp split. Also, there is a point to be made here about the angle of the femur. The lower articular surface of an Australopithecine humerus is human-like. So, humerus. It says a humerus. Oh my gosh. This is not a humerus. This is a femur. The humerus is the bone in your upper arm. But, okay, so by lower articular surface, that refers to the bottom part here. That refers to the sort of the top part of your knee, which is the bottom part of the femur, right? So, the angle of the condyles on a human femur, the condyles are these protrusions here. The angle of the condyles on a human femur and on an Australopithecine femur are similar. Chimpanzee, it's not. And, well, it's less similar to a human's and an Australopithecine's. The size and shape of these condyles, coupled with the angle of the femoral head, so look at the human femur. It's almost a right angle. Australopithecus, almost a right angle. Pan, it's an obtuse angle. So this angle, combined with the shape of these protrusions here, creates, in humans, an inward sloping femur. So our femurs tend to go towards our center at our knee. On a chimpanzee, however, the femur goes more or less straight up and down. This angle helps us maintain a center of balance. It accommodates our large thigh muscles, which help propel our legs during walking. And it's something that we see in Australopithecus. Again, it's another good piece of evidence that Australopithecus is on our side of the human-chimp split. Also, There's the upper articular surface of the tibia to be taken into account. Humans, so the upper articular surface just means where the bone comes together. So the tibia, we have Lucy's tibia, and we of course have many human tibias. Human and Australopithecus tibias have a medial condyle. Well, this is called a medial condyle. What's this called? Well, they have a little condyle here on a bump in the middle. That's all you need to know. That's a little bump. Chimps, they have a bit of a sort of elevation, but they don't have a bump like we do and like Australopithecus does. And what these bumps do is they help to stabilize the connection of the femur and the tibia. They sort of make the two bones come together in a more stable configuration. And what that's good for is bearing weight on the leg. You can also look at the articular surface of the tibia here, and you can see that on a chimpanzee, the interior protrusion extends more than the exterior protrusion on the outside of the knee. However, on humans and on Australopithecus, this exterior, or I guess lateral protrusion here, is more suited for bearing weight. So on Australopithecus, it's nice and thick. On humans, it kind of extends out. And what this is an adaptation towards bearing weight on this angled femur. Chimps don't have to bear weight on an angled femur. They walk about just fine on their knuckles, so they don't have any adaptations like these. Altogether, it seems to indicate that Lucy was adapted for bipedal locomotion on the ground, and her curved fingers seem to suggest that she was still hanging out in trees, so she's a transitional character. And this is Oreopithecus actually here. And remember, he's not all that closely related to humans, but I want to show you the shape of his pelvis. He was a biped. He has a nice broad ilium. Let's talk about another piece of evidence that Australopithecines were bipedal and therefore on the human side of the human-chimp split. Laetoli footprints. When they were discovered, they were the best evidence for Australopithecine bipedality. They were discovered in 1976 by Mary Leakey. They were dated to 3.7 million years ago, and there were three hominids, three distinct hominid individuals leaving tracks in the mud, as well as tracks from other animals as well. And Tim White was a graduate student with her at the time, so he was out there doing that. He goes back a ways. So the features of these footprints, 3.7 million years ago, that was the oldest evidence of bipedality until Ardipithecus had been found. These footprints, 3.7 million years ago, they were made by Australopithecines because there were no humans back then. There were no members of genus Homo back then, so they must have been made by Australopithecines. Let's look at the parts here. So number one feature you should take note of is the big toe. This big toe, or also you can call it the hallux, it's separated from the foot significantly. So that might mean that it was still maybe a little bit mobile. You know, chimpanzees, they have basically they just have thumbs on their feet instead of big toes like us. So what this suggests is that by 3.7 million years ago, that thumb, which would have been going out here, had actually started to move in and gone into line with the rest of the toes, and would have started playing a role in pushing our legs forward when we push off the ground as we walk. Also, these footprints are interesting because the heels make the deepest impression, which means that the feet were striking the ground heel first. Bipeds do that. When chimpanzees walk, they tend to strike the ground with the side of their foot first because they've got a little bit of back and forth, side to side motion as they walk, as they have to kind of swing their legs forward. That's if they go about bipedally. So the deepest impressions are not here laterally, but rather here in the back on the heel, meaning that the people who were walking Laetoli were walking heel first. And finally, there's an arch here. So this is supposed to be a bracket showing you the arch, that there's actually an arch in this foot, which is something that you only see in Homo and Australopithecus. So it's something that is indicative of a bipedal locomotion. So bipedality, as sort of the key characteristic of the human side of the human-chimp split, this adaptation first appeared in apes in the Rift Valley of Africa. So let's talk about that. It would have the Australopithecines, as we know them, I guess not counting Ardipithecus, lived from 4.5 million years ago to about 1.5 million years ago in the Great Rift Valley in East Africa. So if we look at this map of Africa and then where all the Australopithecine fossil sites are, we see that they all fall into this general area. This here is actually the outline of the Great Rift Valley. This could also be just because this is where people have been looking. Since the 60s, when the Leakeys started to find a lot of fossils in the Rift Valley, the Rift Valley has become the center of the hunt for human ancestors. Some people have looked in different places, like here at Bahr el Ghazal, where they have found some Australopithecines as well. So we don't have the full picture yet, and there's a certain bias being represented here in focusing the search in just East Africa, but there also seems to be plenty of evidence to suggest that this zone of Africa is important for our evolution. So let's talk about it some more. It's called the Rift Valley. A rift is a tear, and so the Rift Valley itself is basically just a tear down the side of Africa. So they have a western branch and an eastern branch, and they're in an Ethiopian rift. Really, it's just a point where two tectonic plates were moving away from each other, one going this way and one going that way, and they were being pulled apart. So this process, this movement of the tectonic plates, must have been going on for tens of millions of years, long before humans evolved. So during this period, as the tectonic plates are starting to move, most of Africa is a dense forest. I know you think of Africa as a dense forest now. People always think of the jungle when they think of Africa. But really, that's not the way contemporary Africa is. Although, several million years ago, there was a lot more forest in Africa, right? But partly because of the movement of these tectonic plates, creating valleys and new mountains and creating new bodies of water inland, and because of bodies of water forming even farther away, the Mediterranean Ocean, which would be up here, the Mediterranean Sea, the Red Sea, Gulf of Aden, all these bodies of water are also forming. Things are moving around in other parts of the world, causing the climate in other parts of the world to change and having sort of a chain reaction and causing the climate to change in East Africa, this forest couldn't survive. Because of the Rift Valley pulling apart and because of these climatic changes going on around the world, the atmosphere, well, I guess the atmosphere, the climate, the environment of the Rift Valley between 20 and 15 million years ago started to dry up, started to get hotter, started to demonstrate greater variability in altitudes, creating mountains, but for the most part, we're interested in the valleys, a big change in altitude there. And with this came different patterns of water dispersal and different patterns of erosion. So the whole landscape was changing, and the forests started to recede. What replaced the forest was something called savanna mosaic. And what a savanna mosaic is it's a sort of patchwork quilt of environment. There are forest patches, there are grasslands patches, there are patches of wetlands, and there are bodies of water. And this is the kind of environment in which the Australopithecines evolved. And this is the kind of environment in which our species evolved. So if you want to understand human evolution, the first thing you have to do is you have to look way back before humans and chimps split, you have to go way back 20 million years and start with the movement of continents, and then how that affects the weather, how that affects the climate and the environment, and then you have set the stage for the evolution of Homo from Australopithecines. So here are four kind of savanna images. As you can see, there are sort of dense spots, and there are trees, but there are also wide open spots of grass. So, this is where you see all your favorite African animals, lions and elephants, chimpanzees. Some chimpanzees are savanna dwellers. There's a lot of diversity of life in these parts of Africa, in these environments. And this was also, again, let me stress, the environment in which bipedality evolved and the environment in which we evolved. So the Australopithecines were descended from jungle apes, forest apes. When those forests went away, the apes who survived were the ones best suited for the savanna mosaic. Those were the Australopithecines. Chimpanzees and gorillas tended to stick to the forests, and so they survived and they diversified and adapted there. But then their relatives who adapted to the savanna mosaic became the Australopithecines. So the robust and the gracile sort of found different niches for themselves. They found different professions in this new environment called the savanna mosaic. And how can we understand these professions? Well, we can understand the professions through the fossil evidence. The graciles have dentition and proportions that are similar to bonobos. That is not to say that they are more closely related to bonobos than anybody else, but it does suggest that they lived lifestyles that would have been similar to bonobos. So here we have a bonobo. This is a reconstruction of Lucy, and then here is a gracile Australopithecine from 2001, A Space Odyssey. If you haven't seen that movie, there are definitely Australopithecines in it. The robusts, on the other hand, they had big teeth and jaw muscles, and they had really marked sexual dimorphism. The males were a lot bigger than females, and that suggests that their lifestyle was more like a gorilla's. Okay? So follow me here. Well, here's the robust Australopithecine. This is the black skull. I talk about this guy and show you a replica of it in the bone demo. And here's a gorilla. So they're definitely not the same creature, but they have similar adaptations to their facial anatomy. They have the sagittal crest, big zygomatic arch, nuchal crest on the gorilla. There's sort of a nuchal crest on the black skull there, a robust Australopithecine. So in this environment, we got the robusts living like gorillas. They're hanging out in shady spots, not moving around a lot all the time, and they're browsing in the woodland, right? So these guys are hanging out in the shady, cool forest all day, not moving around a lot, and they're browsing on vegetables. But the gracile Australopithecines are like chimpanzees. They move from food patch to food patch, and because they're moving around in the savanna, they spend a lot of time under the hot sun. And so they had to come up with ways to deal with the hot sun. And this, again, is a step in our direction, the direction of humans. But we're still got to focus on this bipedality thing. So, as I've said, the woodlands, open plains of the savanna, that's where bipedality evolved. How did it evolve exactly? What were the pressures that caused it to happen? Because, well, monkeys and apes can walk on two legs. They do it all the time. They just are not specially adapted for it. So the question is, if four legs are fine, are just good enough for monkeys and chimps, and they can get up on two legs when they need to, like this guy Ambam the gorilla is getting up to carry things, then what was the pressure that caused relatives of these guys to become strictly bipedal, only bipedal? Well, it's hard to say what the pressure was. I'll put these videos up on the internet. You can watch Ambam here walk around on two legs, and you can also see Natasha walk around on two legs. But getting to what the pressure was, it's hard to say what the pressure was that was selecting for bipedalism. What was the context in which bipedalism was so advantageous that they had to give up knuckle walking altogether? Well, it's probably complicated, and there are at least 7 good reasons to be bipedal in a savanna mosaic context. First good reason is carrying things. You can carry your babies, you can carry food, and you can carry weapons. You can also carry tools, like this little brown capuchin is. Carrying food and babies is probably the really big thing. Because if you're mobile, if you've got to keep moving from food patch to food patch, either you've got to bring your family with you, or you've got to bring your food to your family. So carrying is a big deal if you've got to do a lot of traveling all day long. Vigilance. See, this girl, she can see over the grass. She doesn't look like she's paying attention, but she can see over the grass if she wants. That means it's easier to spot predators out on the savannah, where there often is a lot of tall grass and low shrubs. Also, being bipedal puts this girl's head and body up into the wind. And this is really important because it's hot on the savannah. It's not like hanging out in the woods all day where, okay, it gets hot, but you're probably not going to get cooked by the sun. Out there in the grasslands, these chimps could get cooked by the sun. These chimps, they're not chimps. I'm talking about Australopithecines, but they could get cooked. So putting your body up is a way to disperse heat. Versus a chimp who's got this big broad back, and it's just being beat down upon by the sun. Of course, four-legged animals also have to deal with this, and there are a lot of four-legged animals on the savanna, but they've dealt with heat dispersion in other ways. A fourth thing is that bipedalism is more energy efficient than walking on four limbs or knuckle walking. And if you've got to do a lot of traveling over long distances all the time, then it really does pay to be energy efficient, especially if your food is going to exist in patches that are dispersed throughout the environment. And the reason bipedalism is more energy efficient than walking on your knuckles or walking on all four limbs is because, well, you're just moving 2 legs, not 4. The fifth reason to be bipedal is that it increases your display repertoire. So this guy can get up and use his arms to display. Of course, gorillas could beat on their chest and chimps can throw their arms around, but it really helps to be able to pick up a stick and swing it around threateningly. This looks like Kanzi. I don't know. He looks like a young Kanzi to me. Anyway. Sixth reason to be bipedal is because it helps you to forage. Look at Oreopithecus here, not a very close relative of humans, but a bipedal ape foraging, right? It's the same reason giraffes have long necks. You can reach up and you can get things. You can reach into trees or bushes that might not be able to support your weight if you're a large animal like a gorilla or a chimp. Review. Carrying, vigilance, heat dispersion, energy efficiency, display, and foraging are 6, but there is a 7th. Okay, so to understand this 7th big advantage of being bipedal, we have to start with brain size. So we know we had bipedalism at about 3.8 million years ago with the Laetoli footprints, and if we like Ardipithecus, then we've been bipedal for 4.4 million years. By we, I mean human ancestors. I mean our side of the family after the human-chimp split. But the really big brains did not appear until about 2 million years ago. So why is that? It has something to do with bipedality. I want you to keep in mind, as I try to explain this to you, that as Raymond Dart said, bipedalism came first and then brain expansion came after that. And this lady, Dean Falk, extrapolated upon that concept in order to argue that bipedalism actually allowed us to evolve big cortexes. That the only reason why our ancestors could get such huge brains was because we were bipedal first. So how does this work? Well, okay, I'll tell you what Dean Falk did. She got endocasts. That is the not quite fossilized brains, but rather the fossilized impressions of brains left inside of crania. She got them for robust Australopithecines, for gracile Australopithecines, and for Homos. And what she did is she analyzed the pattern of blood vessels in the crania. If you are a robust Australopithecine, you have a blood vessel shaped like this. It's sort of a low Y-shaped vessel. And what happens here is hot blood from inside the brain gets pumped out and it goes into here. These blood vessels are close to the back of the neck, they're close to the skin, and so sweat that's evaporating from the skin can cool this blood off. It drains into the jugular foramen and it goes and cools the body. Gracile Australopithecines and Homos have a very similar system. It's differently shaped and it does different things because of its different shape. But the main thing that we do with these is the same. That is, hot blood from inside our brain gets pumped out close to the skin, is exposed to cooled skin that's been sweating, and then pumped back into the body where it can cool the body. So just identifying the distinct patterns of blood vessels in the backs of the skulls was pretty interesting. It was more evidence that robusts were an offshoot of Australopithecines, that they had evolved from Australopithecines, went in a different direction. And it's more evidence that Homo and the gracile Australopithecines were closely related. Moreover, though, there is a special function that this particular shape of blood vessel that's shared by the graciles and by Homo species, there's a function that this shape does. The shape, we can call it a transverse sigmoid shape. Transverse is just referring to the fact that it goes across the back of the skull, thus exposing itself to more cooling area. And sigmoid because it's slightly S-shaped, I guess. The special thing about the transverse sigmoid version of these blood vessels, the version that is shared between the gracile Australopithecines and our genus Homo, is that, well, when you exert yourself, this area here, the blood changes direction through this area. So what happens is this blood that's been cooled close to your skin actually gets pumped backwards and directly into your hot brain. So if you're really exerting yourself, and say you're doing it under the hot sun in the savannah, well, that's when you might have heat stroke. And don't forget, the brain is a very hot organ. The brain uses more energy than any other organ. It uses more energy just on an everyday basis than a marathon runner's legs use during the course of a marathon race. And as it uses this energy, it produces a lot of heat. So having a big brain is actually risky, because if you have a big brain that produces a lot of heat and you don't have a good way of getting rid of that heat, then you're basically just setting yourself up for heat stroke. You're setting yourself up to die because of your big brain. So you can't really have a big brain unless you've got a really efficient cooling system for that big brain. And this transverse sigmoid system that when under exertion, pumps cool blood directly into the middle of the brain. This is an adaptation for big brains. This transverse sigmoid system makes big brains possible. The big brains themselves are advantageous because they allow us to think about the world in different ways. They allow us to remember our allies more. They allow us certain access to complex social forms. They allow us to make tools, but you can't have all that unless you've got this other thing going on here, this transverse sigmoid shape to your vessels. Key, this system only works if you're bipedal. Gravity plays an important role in pooling the blood through these vessels. So the point here, Dean Falk's point, is that bipedality was a crucial step in the evolution of big brains. That we could not actually have afforded to have these big energy-sucking, heat-generating organs inside of our skulls, as neat as they are and as complex as they allow our behaviors to be, we could not have had them if we had not become bipedal first, if we had not changed our bodies before we changed our brains. All right, well, that's it for this lecture. We're going to talk about Homo genus in the next lecture, getting ever closer to Homo sapiens. I'll see you then.